Hi everyone, Dr. Robin here, and today it's time for a new series that I call Dr. Robin Answers Questions. In this series, I'm going to, you guessed it, answer questions. In an ideal world, these would be questions that you post in the comments on my videos, but for now, we're going to start with questions that often pop up in my class, ones that don't necessarily fit into my normal videos. In this video, I'm going to be answering questions about two-point equations. What is a two-point equation, you ask? Well, it's an equation with a specific form. The two you're most likely to run into during Gen Chem are the Clausius-Clapeyron equation and the Arrhenius equation. In this video, I'm going to answer 3 commonly asked questions about two-point equations. Are you ready? Let's start with question number 1. Where did that two-point equation come from anyway? So when you're taking general chemistry, you're likely to see 2 different equations that are somehow both called the Clausius-Clapeyron equation, and 2 different equations that are both called the Arrhenius equation. Students often find this very confusing. For example, this is the first version of the Clausius-Clapeyron equation that many students encounter, and this is what we call the two-point form of the Clausius-Clapeyron equation, which I introduce later. How in the world can these represent the same relationship between the quantities involved? To understand, let's go back to this form of the Clausius-Clapeyron equation. As a reminder, this is the vapor pressure of the solution, this is the gas constant, this is the temperature, and this is the enthalpy or heat of vaporization. But what about this C? This is a constant. If you've taken calculus, you might remember about integration constants. This is one of those. If you haven't taken calculus, just know that this is something that doesn't correspond to an easily measurable physical quantity. So how can we know what it is? Well, with the two-point equation, we don't have to know. So again, how do we get there from here? First of all, let's rearrange this equation so we have that pesky constant on one side, and we'll put everything else on the other side. Now, I want you to think about how this would play out, not in a generic sense, but in a very particular case that I'm going to call case 1, where our temperature is T1 and the corresponding vapor pressure is P1. So let's plug that information into our equation, and this is what we get for our value for C. Now I know what you're thinking. That doesn't seem helpful, but hold on just a minute. Next up, we're going to think about a second case, case number 2, where our temperature is T2 and the corresponding vapor pressure is P2. If we plug that into our equation, we get this as a value for C. And again, this doesn't seem inherently helpful until you realize that C is a constant. So both of these C values represent the same number. Because that's true, these 2 expressions have to be equal to each other. So here I've taken those 2 expressions and set them equal to each other, and you'll notice that each of these 2 sides has 2 parts, a side that has a natural log of something and a fraction. What I'm going to do now is put all of the natural log stuff together by subtracting the natural log of P2 from each side, and then put all of the other stuff together by adding this quantity to each side. Now we have this equation which we can simplify further. First, notice that both of the fractions on the right side include delta H divided by R. I'm going to factor that out like so. In order to understand the second thing I do to simplify this equation, you need to think back to your log rules regarding subtraction. Log of A minus log of B equals the log of A divided by B. So currently, we have the natural log of P1 minus the natural log of P2, and that equals the natural log of P1 divided by P2. That gives us this equation here, which is the two-point form of the Clausius-Clapeyron equation. So I just showed you how to find the two-point equation for Clausius-Clapeyron, but you could absolutely use the same trick to transform the normal Arrhenius equation into the two-point form. So on to our second question, probably the most asked question I get. For the Clausius-Clapeyron equation, how do you know which one is T1 and P1 and which one is T2 and P2? And for Arrhenius, how do I know which one is T1 and K1 and which one is T2 and K2? Well, the answer is pretty simple. It doesn't matter. So I tell students this, but they don't always believe me. So let me show you mathematically why it doesn't matter. I'm going to use the Arrhenius equation to show you, but you could easily do an equivalent proof for the Clausius-Clapeyron equation. So here is the two-point form of the Arrhenius equation. Let's say we're examining rate constants for a reaction at 2 different temperatures. At temperature X, our rate constant is A. At temperature Y, our rate constant is B. Let's say we pick temperature X, rate constant A to be condition number 1. In other words, T1 is X, K1 is A, and then temperature Y, rate constant B is going to be condition 2. When we plug this information into the formula, we get this. Now, of course, we don't have real numbers, so we can't actually do any calculations, but that's okay. I intentionally used variables instead of real numbers. So let's hold on to that for a moment. We'll get back to it soon. Now I want you to imagine that instead we're going to do the opposite. We're going to pick Y and B as condition 1, so T1 is Y and K1 is B. And then X and A are going to be our T2 and K2 respectively. Let's plug those values into our equation and we end up with this. So now I'm going to take these two equations that we derived previously and I'm going to show you that they are equivalent. First, we're going to use our log rules. This time, the one that shows that the log of B over A is equal to the negative log of A over B. If we plug that into our blue equation, we get this. Next, remember that 1 over X minus 1 over Y is equal to negative the quantity 1 over Y minus 1 over X. Again, let's plug that into the equation, which gives us this. Notice that we have negative signs on each side of the equation, and those will cancel each other out. And now compare what's left with the green equation. It is, in fact, the same. So this is why I didn't use numbers for this proof. If I'd used actual numbers, you might think it was a fluke of those particular numbers. By using variables, you could see that this will work for any numbers. And again, remember that even though I showed you that this works for the Arrhenius equation, you could also check to make sure that it works for Clausius-Clapeyron. Onwards to question number 3. This is one I get from people who watch my videos who aren't in my class. And that is, why do you use a different 2-point equation than the one in my book? Actually, the first time I heard this question was when I asked it. I had just started teaching out of a different book than the one I taught with previously. This was right after I switched from my first school to my second school. And I noticed that they had different versions of the 2-point equation. So here are 4 different versions of the 2-point form of the Clausius-Clapeyron equation, and I am 99.999% confident that your chemistry book uses one of these. So what I'm going to do now is show you how all 4 of these versions are equivalent to each other. To do that, we're going to use 2 relationships that I showed you in the answer to the previous question. First of all, the natural log of P1 divided by P2 is equal to negative of the natural log of P2 minus P1. And second, 1 over T2 minus 1 over T1 equals negative of the quantity 1 over T1 minus 1 over T2. So let's start by comparing these first 2 equations. You can see that the top equation has this quantity in parentheses, which is equal to that. Let's plug that in here. Now, let's move this minus sign outside of the brackets, and look, we've got the second equation. These 2 equations are equivalent to each other. Next, let's compare the first and the third equations. Notice that the first equation starts with a natural log of a ratio, which as you can see is equal to this. Plug that in and we get this. And then divide both sides by -1 and we get equation 3. Finally, let's compare the first and the last equations. Again, we're starting with a natural log of the ratio of pressures, which is equal to this. And we have this quantity in parentheses, which is equal to that. And so we plug both of those into the first equation and we get this. All we have to do now is cancel out the negative signs on both sides of the equation, and you can see that the first equation is equal to the last equation. So now we've shown that all 4 of these equations are equivalent. And you could do a similar proof with the Arrhenius equation, of course. So okay, those are the 3 questions about 2-point equations that I get asked about a lot. How we find the answers to these questions can all be summarized in one simple word: math. The reason we want people to take pre-calculus before taking general chemistry is that we want them to be proficient with log rules and such. The more you play around with math, the more comfortable you will be finding answers to questions like these. So that's it for this set of questions. If you like this video, why don't you click that like button down there and subscribe to my channel. If you have other chemistry questions, please drop them in the comments below. Just to be clear, I won't answer your homework problems for you. I have videos that can help you figure out the answers yourself. I'll drop a link to my Gen Chem playlist down below. But if there are questions that didn't get answered in your chemistry lecture or my videos, please let me know and maybe they'll appear in the next Dr. Robin Answers Questions video. I hope this was helpful and I look forward to seeing you again soon.